In this video, we'll discuss the derivative property of convolution. Because all the systems that we're working with are linear and time invariant, then we're able to say the following. Given that x of t convolved with h of t equals y of t, then if you take the derivative of either x or h, x derivative of t convolved with h of t, for example, then by having taken the derivative of one of the two original functions, you wind up with the derivative of the output. And so that would also mean that x of t, it doesn't matter which one you take the derivative of. If you take the derivative of h of t, you get the derivative of y of t. And funnily enough, if you take the derivative of both x and y, of both x and h, you wind up with the second derivative of y. And the reason why it's useful to know this property is that you can exploit it to make some rather complicated convolution problems a lot easier. So let's see what we mean by that. Suppose you've been asked to convolve this signal x of t, and let me just sketch that in. Let's make that a square pulse like this from 0 to 1. Let's say you've been asked to convolve that with something like this triangle function. So t, this will be h of t. And let's say that looks like this. So I've been asked to convolve those. And the ironclad way of doing this is to use the convolution integral, which says that y of t equals integral from minus infinity to infinity of x of tau times h of t minus tau d tau, where tau is some dummy variable. So that formula will work, but it involves some calculus and some juggling some variables and so on. So if there's a shortcut we can do, then that might be useful. So here's the shortcut we're gonna do. Instead of working with x of t convolved to h of t, we're gonna work with the derivative of x of t. So in our case, the derivative of x of t is going to look like this. There's, for all of time basically, the x of t function is a constant, which means that its derivative is 0. And its derivative will be 0 everywhere except right at the edges where it steps up and it steps down. And at those points you have a discontinuity. And at those points, the discontinuity is an impulse. Okay, so this will be x prime of t. And those are both impulses. This is an impulse with area 1, and this is an impulse with area -1, and they're located at times 0 and 1 respectively. So that's the derivative. And we're going to convolve that with h of t. So instead of doing x convolve h, we'll do x derivative convolve h. And the reason why that's useful is that when you convolve with an impulse, we learned, you just get a copy of your signal. So for example, if I convolve h with that first impulse, I'm just going to get a copy of h. So let me go ahead and draw that. I'll draw that there. I will get a copy of h. Oops, let's see if I can draw that a little tidier. Okay, so that is from the first impulse. And then when I convolve with the second impulse, I'm going to get a copy of h, but shift it to the right by 1 unit. And because the area of that impulse is -1, my copy of h will be flipped upside down. Okay, so here we go. So that's 1, that's 1, and that's 2. And this is -2, sorry, -1, and there we are. So what I've drawn now is not y of t, but it's the derivative of y of t. Okay, because I convolve derivative x with h, I get my answer, which I was able to do by inspection, is y of t. Sorry, is derivative of y prime of t. Okay, but what I want is y of t. So if I want to get y of t, I'm going to have to integrate this. So let's see how that works. Right here, the equation of the line right there is 1 minus t. And over here, the equation of this line is t minus 2. So let's see what we're going to do. We're just going to integrate that to get y of t. So for negative time, I have 0. There's nothing to integrate, so I'm just going to get 0 again. All right, let me label my axes, y of t. So for negative time, I'm going to have 0. Let's do this in blue. Then between t equals 0 and t equals 1, I'm going to have the integral of 1 minus t dt, which will be t minus 1/2 t squared. So let's go ahead and draw that. That should look something like this. Let's see if I can get that right on the first try. Okay, and that y value should equal 1/2, because when I substitute in t equals 1 into the equation, I get 1/2. Alright, and then from 1 to 2, I'm going to have the integral of t minus 2, which will give me 1/2 t squared minus 2t plus a constant. And I can work out that because I know that that function has to start at the same point. I know that when t equals 1, in order to be continuous with the previous segment, I know that when t equals 1, that this function has to equal, so if I let t equals 1, that function has to equal 1/2. So let's see, that's 1/2 times 1 squared minus 2 times 1 plus the unknown k has to equal 1/2. And let's see, so 1/2, so that means k equals 2 in this case. So putting it all together, that is going to look like this. And so this line will have the equation of t minus 1/2 t squared. And this line will have the equation of 1/2 t squared minus 2t plus 2. Okay? And so there we are. We were able to get the convolution of x and h, but we did it in an indirect method. Right? We started by working with the derivative of x. We were able to get that convolution by inspection, and then all we had to do was take its integral, and we're done.